In this video, I'll derive a formula to calculate the length of a curve given as a function y equals f of x. For a curve like this one, that's made up of a bunch of straight line segments, it's easy to calculate the length just by using the distance formula to find the length of each line segment. The distance formula says the distance between 2 points, x1, y1, and x2, y2, is given by the square root of x2 minus x1 squared plus y2 minus y1 squared. Applying this formula to the first line segment, connecting the points 1, 2, and 2, 3, we get a length of the square root of 2 minus 1 squared plus 3 minus 2 squared, which is the square root of 2. The length of the next line segment can be calculated similarly. And the next piece has length 2. We don't even need the distance formula for that one. And the last line segment has a length of the square root of 5. If we add up all the lengths of these 4 line segments, we get a total length of the curve of 2 times the square root of 5 plus the square root of 2 plus 2. We can use the same process to approximate the length of any curve by dividing it up into n small pieces and approximate the length of one small curved piece with the straight line segment and using the distance formula to calculate the length of these line segments. In this picture, the curve is divided up into 9 subintervals. I'll label the corresponding points on the x-axis x0 for A, x1, x2, all the way through x8 and x9 is B. And I can label the points on my curve. So here's the 6th point, P6, has x-coordinates x6, and then y-coordinate will be f of x6, since my curve is given by the equation y equals f of x. More generally, I have n subintervals, and I'll label an arbitrary point p sub I. The point before it is then p sub I minus 1. And the length of the I segment is given by the distance between p sub I and p sub I minus 1. So that's the square root of x sub I minus x sub I minus 1 squared plus f of x sub I minus f of x sub I minus 1 squared by the distance formula. The total length of the curve can be approximated by adding the lengths of all these line segments up. So that's the sum from I equals 1 to n for the n line segments of these lengths. This is starting to look a little bit like a Riemann sum because of the sigma sign, but it's missing the delta x that I usually have out here. So I'm going to use a trick. I'm going to multiply each term of this expression by x sub I minus x sub I minus 1 divided by x sub I minus x sub I minus 1. This doesn't change the value of my expression, but it does introduce a delta x over delta x into my equation because delta x represents the width of a subinterval, and that's equal to x sub I minus x sub I minus 1. Now I'm going to suck the factor in the denominator inside the square root sign. Notice I have to square it when I pull it inside the square root sign. Now I'm going to rewrite my fraction inside the square root sign. Now this first fraction is just 1, and this second fraction can be rewritten with a single squared sign. And this second expression should look familiar to you. It's the expression for the slope of a secant line. And if xi and xi minus 1 are very close to each other, the slope of that secant line is very close to the slope of a tangent line at a point in that interval. In fact, you might recall that the mean value theorem says that the slope of the secant line is actually exactly equal to the slope of a tangent line for some point, I'll call it xi star, in that interval. So I'll rewrite my expression for the approximate length of the curve. And since xi minus 1 can be written as delta x, I have a Riemann sum here. So if I want to find the exact arc length, I just need to take the limit of this Riemann sum. This is the limit as the number of intervals goes to infinity. We know that the limit of a Riemann sum is given by an integral. So the arc length is given by the integral of the square root of 1 plus f prime of x squared dx, starting from the first x value of a to the last x value of b. And so we've derived a formula for arc length. Sometimes this formula is also written with the alternative notation of dy dx instead of f prime of x. Let's use the arc length formula to find the length of the curve y equals x to the 3/2 between x equals 1 and x equals 4. That's this section of the curve drawn. Here's the general formula for arc length. And since dy dx for our curve is 3/2 x to the 1/2, we get that arc length is the integral from 1 to 4 of the square root of 1 plus 3/2 x to the 1/2 squared dx. After simplifying a little bit, we can use u substitution to rewrite this. So we get the integral from 13/4 to 10 of the square root of u times 4/9 du, which integrates to u to the 3/2 divided by 3/2 times 4/9 evaluated between 10 and 13/4, which after some computation works out to 1/27 times 80, the square root of 10, minus 13, the square root of 13, or approximately 7.6 units, which seems about right based on the graph, taking into account the fact that the scale here is by 2's on the y-axis. In this video, we found the formula for the arc length of a curve. If the curve stretches from x equals a to x equals b, then the arc length is given by the integral from a to b of the square root of 1 plus f prime of x squared dx.